the function f of x equal to absolute value of x. If you evaluation f of x at 0, then we will get f of 0 equal to absolute value of 0 is 0. And if we take the limit of f of x as x approaches to 0, is the limit of absolute value of x as x approaches to 0, and it gives us the answer is 0. So you can conclude that the f of 0 equal to the limit of f of x as x approaches to 0. And remember definition of the continuous function. If we have this, that means the function f is continuous. So the function f of x equal to absolute value of x is a continuous function at 0. However, it is not differentiable at 0. But if we have the function is differentiable at a point A, then the function f is continuous at A. That is the theorem number 4. So the function f is differentiable at A, then f is continuous at A. This is true. But if we go opposite, the function f is continuous, then you say f is differentiable. This is wrong. The example for wrong direction is the absolute value of x. Now we want to show that the function f is differentiable at A, then f is a continuous at A. We want to show f is continuous at A. That means we want to show that the limit of f of x as x approaches to A equal to f of A. And this is the same thing as we want to show that f of x minus f of A approaches to 0. So this is what we want to show. Now let's look at what we have. What do we know about the function f is differentiable at A? So the function f is differentiable at A, then by definition of differentiable, f prime of A equal to the limit of f of x minus f of A divided by x minus A as x approaches to A exits. Okay, and then the next step, I calculate this, and this is the difference between f of x and f of a. That's what I said before. This is what we want to show. Okay, we want to show is equal to 0. So then I take the limit when x approaches to a. I multiply x minus a and divided x minus a. Then I don't change the original statement. And then because we have a multiply, then we can separate the limit. This is equal to f prime of a because this is by definition of the differentiable, so which is from here. And the second one, what all we need to do is just plug the x into x minus a, and we have a minus a, and that's why we have 0. So we have the answer is 0. And then I go back and I look at the limit of f of x as x approaches to a. So remember before, if we want to show that f is continuous at a, we want to show that the limit as x approaches to a of f of x equal to f of a. So I calculate the limit of f of x as x approaches to a first. What do I do is I add and subtract f of a, then I don't change the original problem. And then I separate them. So this is the sum right here. So I take the limit of this and then take the limit of that. So for the first one, the function f evaluate at a, it will give us a constant. So the limit of the constant is a constant, is a number. The limit of the second part is 0 because we just show here. This is from here. Okay, so when we add them up, it's equal to f of a. So remember what we say? We want to show that right here. We want to show that the function f is continuous. That means that we want to show that the limit of f of x as x approach a equal to f of a, and that's it, right? Okay, so we can conclude that the function f is continuous at a.